All right, so let's take a look at this standard linear solid model, or the Maxwell-Zenner model. So here we have a spring that's in series with our Kelvin-Voigt model. If we see it here, I think I accidentally deleted this, so bear with me. Again, this is the benefit of a live lecture. Everyone wants that. I had to delete some previous work. Let's get rid of this. Let's get rid of this. Don't look. Spoilers ahead. Let's get rid of this guy. And all right, now we could actually keep our... all right, let's just erase this by hand, I guess. Let me switch my... There we go. All right, let's restart, again, our discussion here. So we're going to look at our standard linear solid model, and we're going to have essentially our spring that's going to be in series with our Kelvin-Voigt model. So we actually already have our expression set for the Kelvin-Voigt, but we're going to add some complexity here. So again, for this model, the standard linear solid, we have in series a spring component and a Kelvin-Voigt. So we should know that our stresses are going to be equal and our strains will sum. We already have our expression for how we can express the strain of our spring component, and we can look back to what we previously derived way back up here for our Kelvin-Voigt expression. So specifically that we have this basically Kelvin strain dot plus, let's go ahead here, or actually equals this minus eta, and then divide that by our E. And we're going to call, instead of this KV, we're going to call this the E2. So we'll make an edit a little bit later on. And our strain, exactly, our actually we're going to rewrite that strain dot for KV. And then we're also going to add now our SLS solid over this. Let's just kind of do the math on this live here. And we can go ahead and divide that out by our E, basically this E2. So here we go. Excellent. So we have our expression. So we can now start to write out the full strain. So yeah, we can bring this down. Let's bring this down so we can work with it a little bit nicer here. Excellent. And now let's start to rewrite and plug that in. So we've got E prime of KV, and actually we could rearrange our original expression for strain as well, because we see that we're going to have to work in that E prime, we're going to have to get rid of that E prime KV at some point and write it in terms of SLS and all those good things. So our strain of SLS, we're going to substitute in the E prime of the KV, or the EKV, epsilon KV, excuse me, and we're going to substitute and plug in directly now for E prime KV is equal to E prime SLS minus E1 prime, which is going to be our sigma SLS divided by E1. Plus, again, so we're going to add on plus sigma SLS. So we add on there. Let me get my sigma SLS over E2. And then we're also going to add on sigma SLS over E1. A nice, disgusting looking equation. but we have our constitutive equation right here. So you could actually stop here and wrap it up and basically proceed with integration and looking at the creep and your stress relaxation response. But we can make our lives a little bit better by kind of rearranging some values. So what we're going to do is we're going to pull out our function and just put all of our, this is a good way to write your constitutive relationships. I would put all of the strains on one side and put all of the stresses on one side, where you have your dots and your, you could have even some scenarios where there's double dots and all of those good things. So we're just kind of rearranging and putting our terms in a little bit of a nicer kind of format here, so that we can kind of see our final expression effectively emerge from this. And now all we have to do, we can now just multiply the entire function by E2 over eta in order to make it, again, just a little bit nicer. So again, we're gonna multiply out here, and then basically obtain our function and make sure that it matches relatively well with the function that we see on our screen in the SLS model. So this will be a little bit nicer. Once we multiply through the math, in order to obtain a very similar expression to what we see here in the notes. So let's go ahead and multiply everything by this E2 over eta term. So E2 divided by eta, that cancels out, leaves a nice E prime SLS on the first term, plus our E prime SLS E2 over eta for the next term right here. So let's write this out. Epsilon, we need that epsilon, actually, that epsilon SLS over here, and then sigma stuff over E1, and then again the E2 term disappears, and the eta term disappears, and then now we have SLS over eta 2 here, and now we can start to make our term look a little bit nicer. And there we got it. So it looks exactly the same. And now we can start to proceed with that function. Just note that E2 over eta term on the left side, it needs that epsilon SLS. So, but again, matches. Again, we've got our values. One quick note, at very, very short times, you can approximate that dash pot just to be a solid line. So that would just be a solid line. You can replace that. And at very, very long times, you could replace it as disconnected. So at short times, that's going to trap that Kelvin-Voigt model. And it's not going to allow any, basically strain to be felt there. So you're really just going to feel in that system the strain from basically your E1, your spring. And at very, very long times, that's disconnected. But then you'll feel essentially, you're going to feel the combination in series of E1 and E2. So you can use that to now solve, if you're asked to do so, which you will, to solve essentially for that expression. So that's it.